Hello. In this video, we're going to be looking at solving 2D momentum problems. And we use momentum to analyze what goes on in a collision, because in a collision, the total initial momentum will equal the total final momentum. This is a result of applying Newton's laws to the system. You can do this a few different ways. You can say in a collision all of the forces are internal, and so since there's no external forces present, the total momentum has to be constant. You can also apply the third law to the system, where the force of the collision has to be an equal and opposite for each object, and since they have an equal and opposite force over the same amount of time, they experience an equal and opposite change in momentum, and you can rearrange that to get the total initial momentum is equal to the total final momentum. And that's going to be the main principle you're going to use to analyze what happens in the collision. So let's go through that process. So again, it's going to be similar in how you solve energy problems, where in energy you say total initial energy is equal to total final energy. We'll do a similar thing here. Total initial momentum is equal to the total final momentum. However, momentum is a vector, so you have to be mindful of directions. You have to separate the momentums into their x and y parts and always keep them separate. A lot of times you'll be given velocities in terms of magnitude and angle, so you'll have to use your trig functions to separate them out to the x and y pieces. And you'll look at solving for the momentum of each object in the x and y directions. Total initial momentum of those two objects will equal the total final momentum of those two objects in each direction. And in the case where objects stick together, the total momentum will equal their combined mass times their velocity. And next I'm going to show you the equations you're going to use. And it may seem like a lot, but it just boils down to one, defining momentum, and two, again, just saying total initial momentum is total final momentum in each direction. So first off, momentum is defined as the object's mass times the velocity. The symbol for momentum is lowercase p, mass m, velocity v, and we don't have special units for it. It's just kilograms times meters per second. And your total momentum in each direction will just be the momentum of, say, the first object plus the momentum of the second object. So total momentum in x is the momentum of A in the x direction plus the momentum of B in the x direction. Likewise, total momentum in y is the momentum of A in the y direction plus the momentum of B in the y direction. And we'll employ this, or apply this, to get the total initial momentum is the total final momentum. So, and you'll do this in each direction. So the mass times the velocity in x plus the mass times the velocity in x initially is equal to the mass times the velocity in x final plus mass times velocity in x final. And so you'll have that for both the x and y parts, with the added caveat: if the objects stick together, the total momentum will be their combined mass times their velocity. And the best way you'll see or understand how these work is through an example. So let's do that. So we're going to have a case where we have two objects, A and B. They're both moving at an angle, and they collide and stick together after the collision, and we're going to find how fast they're going and at what angle after the collision. And we'll solve this by looking at the total initial momentum, and then saying, okay, that's the total final momentum, and use that to get the final velocity. And so we'll look at first the momentum of A, separate it out into the x and y pieces, then we'll do momentum of B, separate it out into the x and y pieces. So let's start with object A, and I'll remove everything else from the picture. So there we have object A. It has a mass of 3 kilograms, it's going at 2 meters per second, it's going at down at an angle of 20 degrees off the horizontal. So first we have the velocity in terms of a magnitude and angle. We need to separate that out into the x and y pieces. To get the x part, that's the adjacent side of the angle, so we'll use a cosine. And since it's moving to the right, it has a positive x velocity. And to get the y part of the velocity, that's the opposite side of the angle, so we're going to use a sine, and since it's moving down, it's going to have a negative y velocity. So let's get our momentums. Momentum of A in the x direction is its mass times the velocity of A in the x direction. So we have the mass is 3 kilograms, and we used our trig to get our x component of that velocity, which would be a speed, 2 meters per second, and a cosine of 20 degrees, and it's positive since it's going to the right. Punch that into our calculator, we get something around positive 5.6. And we'll do the same thing in the y direction. Momentum of A in the y direction is its mass times the y component of its velocity. And again, since it's moving down, it's a negative y component, and to get just the y piece, we use a sine to get the opposite side of that angle. And we should get something around negative 2.05 for that. So again, the main thing is, because momentum and velocities are vectors, you have to split them into the x and y pieces in order to properly apply them in a problem. So that's what's going on with object A. Let's look at what's going on with object B. So object B was moving up at an angle, and so we'll have to split this into its x and y pieces. To get the x component, it's the adjacent side of that angle, so we'll use a cosine, and since it's moving to the right, it has a positive x velocity. And to get the y component, it's the opposite side of the angle, so we'll use the sine, and because it's moving up, it has a positive y velocity. And momentum is mass times the velocity. We'll do that for each direction. So the momentum of B in the x direction is its mass times its velocity in the x direction, so 5 kilograms, and its x velocity is positive 3 cosine 30 degrees. Again, it's going to the right, so it's positive x, and we use a cosine to get the adjacent part. You should end up with something close to plus 13 kilograms times meters per second. Do a similar thing for y. Momentum of B in the y direction is its mass times its velocity. So forgive the typo there. We'll do 5 kilograms times plus 3 meters per second sine of 30 degrees. So it's moving up, it has a positive y component, and we to get the y component, it's the opposite side of the angle, so we'll use sine. And you should end up with plus 7.5 kilograms times meters per second. So we have those initial momentums in each direction, so let's add them up to get the total momentum. So our total momentum in x will be the momentum of A in the x direction plus the momentum of B in the x direction, and we'll use those initial values that we just solved for. You should end up with something like plus 18.6 for your total momentum in x. And we do the same thing in the y, where the total momentum in y is a momentum of A in the y direction plus the momentum of B in the y direction. And the important thing here is, since the A is moving down, it's a negative y momentum, and since B is moving up, it's positive. So you always have to be mindful of sign here, and you should end up with something like plus 5.5 or 5.4 kilograms times meters per second. And because we have a case where the objects stick together after the collision, their total final momentum will be their combined mass times that final velocity. And so we have the two masses, 3 and 5, that gives us 8 kilograms. So that means after the collision, the total momentum in x is the 8 kilograms, the combined mass times their final velocity in x, and the total momentum in the y direction after the collision is that combined mass of 8 kilograms times the final velocity in the y direction. So we have their total momentums now from before the collision, and we know that they stick together after the collision. So after the collision, their final momentum, or total momentum, is the combined mass times their final velocity. So what we'll do is take our values for the total momentum in x, apply that down here, rearrange it to get the final velocity in x, and likewise we use our total momentum in y, put that in down here to get the final velocity in y. So let's do that. Total momentum in the x direction initially is equal to the total momentum in x final. So we get those values from, again, looking at what's going on with the two objects before the collision, being mindful of separating our things into their x and y pieces with our trig. And you should get that the final velocity in x is 2.33 meters per second. Do a similar thing in the y direction. Again, forgive the typo here. Total momentum in y initially is equal to the total momentum in y final. So you should get plus 0.68 meters per second for that. If you want, we can also look at this in terms of the magnitude and angle. So let's do that. To get the magnitude of the final velocity or the speed, it's just Pythagorean theorem, x squared plus y squared, and all under the square root. So final velocity in x squared plus final velocity of y squared, all under the square root, should end up with 2.43. And we can employ some trig to get the angle. You can use sine, cosine, or tangent, doesn't really matter. You'll get the same angle either way. If I use a tangent, tangent is always opposite over adjacent. And so if I do the angle with respect to the horizontal, that would be the final velocity in y over the final velocity in x. And if you do that and do the inverse tangent function, you'll end up with 16.28 degrees or thereabouts. So just to walk you through the process again, what we did was the heart of the problem is that the total initial momentum is equal to the total final momentum. And because momentum is a vector, you have to do this both in the x and y directions, and you always keep them separate. So we had two objects moving at angles, so we had to use our trig functions to get their velocities and momentums into their x and y parts. And we solved for the total momentum before the collision, and because they stuck together after the collision, their total final momentum in this particular problem was their combined mass times that final velocity. And since the total initial momentum was equal to the total final momentum, we could use that information from the initially to get the total momentum and divide that by the combined mass to get their final velocity. So I hope you found this helpful, and stay tuned for more videos.